Welcome to our 17th lecture in mathematical finance. So we're currently dealing with the hedging and pricing problem of American options. Let me recall for a minute what we have seen last time. This was so basically we understood the pricing problem for an American option in a complete market. If we want to price an American option, so you recall that the American option, you have the holder of the option has the right to exercise the option at any time before maturity. So we need to determine it mathematically speaking with the process. So the process CT is the payoff you get if you exercise the option at time t. Okay, this is what we studied last time. And if we have now a complete market, so every European option is replicable, we have seen that the price of the American option, so the arbitrage-free price, which we denote here with PA of the American option C, is given by an optimal stopping problem for the buyer, right? So if I buy the option, I want to maximize the payoff I can receive. So I consider the discounted process here as usually denoted with the tilde, and then I'll try to stop it in a way that the expectation under my martingale measure Q is as big as possible. So I am allowed to maximize overall stopping times, which are assumed to be less or equal than the terminal time t. Right? So these are the exercise strategies for my American option. All stopping times which have to be exercised before the maturity of the option t. And we have seen how to solve it. So we know there's an optimal stopping time tau tilde attending the supremum here. And the value of this supremum is given by the Snell envelope of the discounted American option at time 0. Where this here is the Snell envelope so I mean, we developed, our motivation to develop this martingale technique to solve optimal stopping problems was to price and hedge now American option. But you know, in general, this is, I mean, a technique you can apply for any stopping problem. I mean, if it's in the right context. Okay, and now I mean, so do we have derived the price at the time 0? What we can do now, I'm well not giving any details, you can amuse yourself and, well, instead of starting from time 0, you start from another time t and you do exactly the same thing. Just take care of that at time t, everything is a random variable, but it's ft measurable. So there's no issue to generalize the price to obtain also the price of the American option at any time t before maturity. So the arbitrage-free price, if we are at time small t of the American option, now you won't be surprised. You only need to take into account the discounting factor piece or risky asset. Well, it's exactly the same you take all stopping times, which are now assumed to be bigger or equal than t, right? This is what we have assumed here as well, because every stopping time is bigger than 0. Now, if you start at time t, you want that your stopping time is bigger than t and less than capital T. And instead of working with the expectation under Q, you work with the conditional expectation condition on the current time t. Of course, now I need to make one extra assumption, and this is the one that the American option is still alive, so it was not exercised before time t. Right? Because if the option was exercised before time t, it becomes worthless, and the price would be 0. So it only makes sense to talk about pricing of the option at time t if there is still an option. Before t. Right. And so I mean, this looks like a big step, but I mean, from the things you have learned about European option, you immediately know how to do it. You just go through the proofs you have seen and condition everything on t, ft instead of f0. Okay. So this is basically what we have all studied last time already. I mean, the last sentence here is some extra information, but okay. We developed the necessary two last times. And now what we want to understand is the hedging problem, right? So we understood that this is the price for the buyer of the option, which he is willing to pay, or she is willing to pay. Because, well, she can find a way to exercise the American option that this has the value at time 0, which you just determined. But now we want also to understand why a seller should sell this option, or is willing to sell this option. And of course, if we can find a hedging strategy, for the American option, the seller can hedge herself against their obligation faced by having sold this option. And this means, well, why shouldn't she sell the option? So let me start right here with the new headline, so pricing, hedging of American option. So first thing, as for the price, the first thing I need to do is I need to tell you what I mean by hedging of an American option, right? We have defined it for a European one, but you have seen also for the price of the American one and the European one, we use different definitions. So first thing, I need to give you the definition of the price of an American option. And this is definition 517 in the lecture notes. Okay. So as usual, I only want to consider self-financing trading strategies. So we consider a self-financing trading strategy phi, right, consisting of the position in the risk-free asset and in the risky one. And then I want to call it hedging strategy. And here, of course, for the American option, C, if the value process associated to this trading strategy phi at any time t provides a bigger or equal payoff than the obligation I have from the American option. And so this is the seller's perspective. So I sell the option and I have to match this obligation at time t. So CT is the obligation I have to, the money I have to deliver if the buyer of the option exercised the American option at time t, and I want to ensure by trading in the market that I have at least this amount of money. Okay. And well, remark. So the initial value here of VT at V0 of V is the initial capital required to implement here the hedging strategy. Okay. Let me mark this underline. So a hedging strategy for the European one was to say, okay, I really want to match exactly the obligation at the terminal time. Here, this might be too good to hope. I mean, too good to be true. So I'm happy if I somehow can super hedge the option, the American option at any time. And if I can find such a trading strategy, in the best case for the price we already discussed for the American option, then I'm happy to sell the American option. And this brings us to our next proposition, which is exactly the statement. Proposition 518. So indeed, there exists a hedging strategy phi for our American option C such that the initial capital I need to implement this hedging strategy phi is exactly the arbitrage-free price of the American option. And we know already that this price is given by the Snell envelope of the discounted American option with respect to the equivalent martingale measure Q at time 0. Over. We have the following representation of the arbitrage-free price. So, okay, this is by definition, what we already know is that the price can be expressed here as this optimal stopping problem. And now this is the new part, is that it actually can be expressed as the minimal super hedging price or hedging price for the American option. So the minimal initial capital I need to superhedge the American option C. Yeah. So what you see here is the price, the arbitrage-free price of the American option is really the minimal initial capital I need to hedge the option. This is a very nice statement, but okay, we need to prove it as everything. So why is this true? Well, okay, so the proof is basically plugging in everything we learned in the last lectures. So this is just combining the results we know. So first thing we know is, we know, if I look at the Snell envelope of the discounted price process, so the Snell envelope of the discounted American option with respect to the martingale measure Q, we know it's a Q super martingale. Right. Okay. This is if you want to look it up, proposition 512. Okay. And by Dupes decomposition, right? So we know if you have a super martingale, we can decompose it into a martingale part and a predictable non-increasing or decreasing predictable process. So we know that Q at time t is given by martingale part mt and at. Where, as I said, mt is a martingale under Q now, of course. And at is decreasing. So it's not strictly decreasing. It's just, it's non-increasing. Predictable process. And to have uniqueness, we normalize this to say, okay, at time 0, I choose my predictable process to be equal to 0, right? So this means the mt z at time 0 is equal to m at time 0. Okay. Now I say, okay, well, we want to plug in all our knowledge. So we had another statement which was telling me, well, if I consider my optimal, so if tau star, so this is my optimal execution, the exercise time, which were given by the infimum. First time such that Snell envelope equals to the discounted price process, right? This is my optimal stopping time for the American option problem. Then we know, this is what we also have shown last time, that the stop Snell envelope, so if I consider the envelope, so if I take my Snell envelope and I consider the stop version of it with respect to the stopping time tau tilde, this is a martingale under Q. Right. Okay. And if you want to check this out, this was our lemma last time. 5:13. Okay. Sorry. Okay, what does this imply? Well, if I combine now my Dupes decomposition, so the decomposition which I have of the Snell envelope, and the statement that the stop process is a martingale, what do we see is, well, for martingale, the predictable process here has to be constant to 0, and MT, which is a Coulomb martingale, has to be equal to the T, as long as T is less or equal than tau star. Because up to time the tau star, we are martingale, right? So this process here, and this decomposition is unique. So the only way I can decompose a martingale is to say that my process A, my predictable process, is constant to 0. So this means M is equal to my Snell envelope. Now we want to use that my process, my market is complete. So if I have a complete market, sorry. I can represent every martingale as with respect to Schre's integral or self-financing trading strategy, generating this martingale by trading into the discounted price process. We again know this is, I want to check it out again. It's a proposition from a few weeks ago, which tells us, well, if I have a complete market, well, they exist. Self-financing trading strategy. Phi, so this phi as usual. So this is two position, here's a one-dimensional market. Such that, well, at time 0, the initial value here is the martingale. So the initial capital I need for this self-financing trading strategy is M0, and at time t, it's nothing else than, well, my initial value I need, so M0, or the initial capital of this trading strategy, and then I can represent it as a self-financing trading strategy. So since I want to invest here into the discounted price process, of course, I need only to consider the position in the risky asset, because the risk-free one is normalized to 1 by the discounting. Right? Okay. Yeah, so I mean, there was nothing hard in it. It was just putting in all the things we know. So what do we see now? Well, first thing, well, the arbitrage free price of the American option is equal to M0 is equal to V0, right? This was how we derived it. And what do we else get is, well, if we look at the value process of this self-financing trading strategy, this is equal to MT. Well, this is by construction the case. But MT can be estimated from below by MT plus AT. Because it's a process, A is process starting from 0 and then going down. So this is negative. So if we subtract something, then, well, this gets smaller. And now, well, what is this? But this is the decomposition of my Snell envelope, and my Snell envelope by construction dominates the payoff of the American option, or the discount American option. Okay. That's good. Sorry, I forgot here the discounting factor. I did in the notes. Right. Because we're talking here about discounted quantities. But okay, you can reverse the discounting to see that he is indeed a hedging strategy. For my American option C. Okay, that's great. So first thing is, we finished the first part of the proof. We showed that they exist. So this is here the first statement. They exist a hedging strategy for the American option C, and the initial value, so the initial capital we need is exactly the arbitrage free price. So now we are left to prove this second statement, namely that the arbitrage free price is given by the minimal super hedging price for the option C. So this means I cannot find a hedging strategy for initial value or initial capital which is less than the arbitrage free price of the American option. Okay. So let's make a bracket for the second part. So of course, I want to check that I can't do better. So what we do is we take another hedging strategy. So phi bar, which is a hedging strategy. For our American option. Let's see. Okay. So if we have a hedging strategy, this is a self-financing trading strategy. So if we consider the discounted value process with respect to phi bar here, what we know, it's a Q martingale. And well, since it's a hedging strategy, it also has to dominate the payoff of the American option, and this means that the discounted value process associated to phi bar dominates the discounted payoff of the American option. Okay, but now we know that the Snell envelope is the minimal, the smallest super martingale dominating this payoff here. So this is the content of proposition 12 telling me, well, actually I know, that since this is here, martingale is also a super martingale, which dominates the discounted American payoff. So it has to dominate the Snell envelope as well by the minimality of the Snell envelope. Okay. But this means we're actually done. Like we see also at time 0, the initial value, right? In particular, this equality holds for the price at time 0. So if we put here price at time 0, we know that this hedging strategy has a greater or equal, requires a greater or equal initial capital than our hedging strategy from the first part of the proof. So it's greater or equal than the price of the American option. So let me write this down. And so this is price of the American option, if you like. And well, so I could, so actually the point which is important here is 0, 0, and this is, oh, sorry, I was missing here Q. And this is wait, there's the red color, green. Price of the American option. Okay, so this concludes our proof that the initial capital I need to super hedge my American option is indeed the arbitrage-free price. Here we are. So let's finish our proof, or in particular, finish the second part. Okay, cool. So we have seen now the buyer is willing to pay this price, this arbitrage-free price, because he can find a optimal exercise strategy to ensure that the option is, willing to pay the price for this option. And we have seen that this is the context of this proposition, that the seller of the option is also willing to sell it for the arbitrage-free price because she or he can find a hedging strategy to hedge herself against the obligation coming from this American option. So that's great. And now one final comment. So you might wondering, so if we call this price here the arbitrage-free price, and the final question I want to answer here in this subjection is, why does this create no arbitrage? Because I mean, I called it arbitrage-free price, but I never told you that this doesn't create arbitrage, which was actually the argument we used for the American, for the European option. So question is, okay. So yeah. Okay. This is market. So this is the question I would like to answer you very briefly here. So let's assume, you sell an option for an American option. So you're a seller of American option, so you get the arbitrage-free price, as we have discussed. And now what you do is, we may assume. So I mean, we of course assume that everyone is trading optimally and rationally, right? So I mean, of course, if someone is not performing, I mean, as he should or she should be, then they might create arbitrage out of stupidity. So what we do is we sell the American option, and we assume that, well, the seller will then take the initial money, or the money he gets, to perform a hedging strategy. And well, okay, so that's my hedging strategy. And well, we have seen how it looks like. So what do we see here? If I do this hedging strategy, my value process, if I stop it at any time, will super hedge the obligation I have coming from the American option. So for all tau supposed to be a stopping time, and has to be less or equal than t. Okay, this. All right, but this is why this is basically the perspective of the buyer. And now, well, what do we learn from this? So let's use our Dupes stopping theorem. Which does tell us, well, if I take now the expected value of this stopped, okay, let me go over to discounted ones. So I take the expected value with respect to the martingale measure of the discounted value process of phi stopped at time tau. Well, this is arbitrary stopping time. Well, since this is a bounded stopping time, I know this is always the initial value of this process, right? And the discounting factor of time 0 is 1, so this is just the value process at time 0 phi. And well, I can also take here if I take the expected value, I have to take it on both sides. So I get here the expected value under Q of the discounted American option at time tau. All right. Okay. And we have here actually equality. With equality, if we choose our tau optimally. So if the buyer of the option exercise optimally, here actually we have equality. And this is what we have proven this time and last time. So hence, what do we observe here? First thing is what's hedging strategy. So even at the optimal stopping time, the value process dominates the payout of the American option. And well, here we have the equality, so let's rearrange this. So if I look at the difference of the value process stopped at time tau star minus the discount American option exercised at time tau star, well, this is 0. Okay, so we have here a non-negative random variable with the expected value of 0. Okay, that's easy. So what do we have here? This is a random variable, which is Q almost surely 0. And since we have an equivalent measure, this is also P almost surely 0. So in other words, if the buyer and the seller act optimally, there's no gain for either side, right? In average. That is there is no risk-free gain for neither the buyer nor the seller. Of course, I mean, of course, if the buyer acts stupidly and exercises at the wrong time, well, then you might create gains for the seller. But you have the rational assumption that all market participants have full information, so they perform optimally based on the given information. Okay. Okay. Let us for the rest of this lecture here today study a bit the most common version of the American option, which are again American put options, and in brackets, as we see, American call options. So let us study American call and put options. Okay. Okay, what do you assume? We're staying in the same setting as before. So so we consider along this, so we have finite markets, or the underlying probability space is finite to ensure that our first and second fundamental theorem at asset pricing hold true. Or for simplicity, we assume we have a one-dimensional market. To make sense of the hedging and pricing problem, well, we want to assume that the market is arbitrage free. And at least for the moment, we also want to assume that it's complete. And as usually denoted by B and S. Given phi. So we have our risk-free asset P, and now here we need to be a bit careful with the interest rate. So why do we have the idea that there's an interest rate growing over time at T? And now I want to assume that my interest rate is greater or equal than 0. Okay, so far I didn't care, but now I start caring. And the reason is it might change the decision you want to make. Because if you have exercised the option, well, you receive some money, and then you want to put it maybe probably in your bank account. And if you lose then money in the bank account because the interest rate is negative, this might change your perspective on the American option by saying, oh, okay, if the interest rate is negative, I want to keep the option alive because I would lose money if I put it into the bank account. So yeah, right. Also for the next chapter, optimal investment or optimal portfolio selection, right? Your decision how you want to trade on a market might change by a negative interest rate. But for the arbitrage free, I mean, for the pricing of the European option and for the, if the market stays arbitrage free or not, this is that you don't care about if there's a negative interest rate or how do we call this object. So it basically could be any, I mean, you don't need to assume that it looks like such a process. And then you have here our one risky asset. Right. Okay. So this is our underlying setting. I've seen it many times. And I want to start with the American call option because this turns out to be simple. So we call. What is an American call option? Well, we denoted it by C call, which is given by here a payoff profile. With, well, C call at time t is, well, what you get if you exercise the option at time t, and then you have here, you get a call option with maturity small t. So right, this is, so you have the right to sell the asset at any time for the given strike price. Okay, and you only will do it if you make money. T. So this is strike price or strike, okay, something which should be non-negative, and maturity without explicitly saying as it's capital T, right? So we model the market up to the time of the maturity of the option we consider. Okay, and well, so right, you have also, of course, an American, and you have also the discounted counterpart. So the discounted call option at time t is, well, you discount the price process and you discount here. So basically you divide by the BT, and that's it. Okay, that's great. Okay, so let's price this American call option here. Okay, you price it. Okay, we developed now nice theory how to price it, and we could run through the things we have developed. But here it actually turns out that this is not necessary. Let us observe the following, which is simple application of Jensen's inequality. So if I look at the discounted price not price, sorry, the discounted payout of the call option at time t. This is given here. Right, so I can estimate it from above by saying, well, the price, so this S tilde t, so the discounted price at time t is nothing else by the martingale property, and the discounted price at time t plus 1 conditioned on the time at t, right? T is a martingale. And well, instead of subtracting k divided by t, bt, we divide by db. And this makes it, I mean, here we use that the interest rate is non-negative. So we just subtract less, making this difference bigger. Okay. Plus bt is bigger than bt. Okay, plus is might be misleading. And so these are the two properties for this. And now we use Jensen. Quality, which allows me to pull in this convex function here. So this is the function I consider plus. So let's pull it in. So I have the conditional expectation of price at discounted price at time t plus 1 minus k minus divided by bt plus 1 plus and conditioned on ft as before. Okay. Well, but what is this? Well, recalling our pricing formula, I mean, we have derived before. Sorry. So what is this here? So the inner part is nothing else than the discounted payoff of the call option at time t plus 1. Discounted, conditioned on ft. Okay. So what do we learn from this? Well, so let's replace this t by a stopping time. So, so take a stopping time, tau in with and of course we want to have exercise strategy, so we take a stopping time which is less or equal than t. We can apply our Dupes stopping theorem. Well, we have here, right, so we replace here the t by the stopping time tau. And now we take the conditional expectation with respect to f tau. So we get here the call option discounted at time terminal t discounted to ft. F tau. Right. Okay. And now we take the expectation with respect to the martingale measure Q again. Right, and then we use the tower property to see this is less or equal than the expected value of the terminal payoff of the American option. So what we see here already is it doesn't matter which stopping time I take, the expected payoff of the discounted American option under the martingale measure Q is always less or equal than if I choose to stop at the terminal time. So in other words, if I maximize over all my stopping times, which are supposed to be less or equal than t, this is always less or equal than if I decide to stop at the terminal time. Okay. Okay. So this is the price actually of so many colors, so I should use them. So this here, if you recall, is nothing else than the price of the American, for the American call option call. Call. Right. So you see one way to optimal stop the American option, the American call option, is to wait until maturity, and we cannot do better. So assuming there is a non-negative interest rate, the optimal exercise strategy for the American option, the American call option, is really to wait until maturity. So let's make it a remark. Mark 519. Assuming so the interest rate is non-negative, the optimal exercise strategy for an American call option is to hold the option until maturity. Right. Of course, this is not true for American put option, at least in general. Otherwise, I mean, would this be true for all American option? There would be no use for them. But so the European call, so the American call options in this sense special, right? So in general means in most of the cases, this is not true for American put options. Right. In particular, this means if you think about one main property for European put and call option with the put call parity, which relates these prices of put and call options. So this put call parity cannot hold for American option, because the price of the American call option and the price of the European call option is the same, but the price of the American put option is unequal to the price of the European put option. So let us now, study how how does the put call parity is affected by changing from European to American option. So let's start with recalling the American put option, the put call parity for European option. So recall. For T, so this, so CET is the price of European call option at time t. And the same manner, CPT is the price of the American put option at time t, right? And then we, I'm not careful here, but of course these both options are assumed to have the same strike, K and material TT. Okay. That's great. And then we had the put call parity, which were telling us. So let's put call parity, which we have seen the proof already. So what this tells us, oh, that was not nice. Make it to a name here, so let me write. Okay. So if I have here, I can read this. So what do we know here? So the price of the European call option at time t minus the price of the European put option is equal to price here. So forward contract. That's a different, it's just a forward contract, and this is the price. Okay, so that's nice. And what we have already seen proof for it. So we actually have seen that this is a model for a property in the sense that all models which fulfill the no arbitrage principles, this equality has to hold true. But here, when we have a finite, so here we have access to all the pricing formulas, so because we have here a finite, arbitrage, free, and complete market. So we can rely on a first and second fundamental theorem asset pricing and use the pricing and hedging with martingale measures. So in the present setting, we can give another proof for it, right? So well, just to recall it, so we know now right, for t at time t, well, so I'm a bit quick here because, well, you have seen the proof and this is rather standard now for you. So you use your pricing formula. So you know you have a complete arbitrage free and finite market. So there is a equivalent martingale measure Q, and the price of an European option can be expressed as the conditional expectation, condition of T, of the payoff of the European option here, of the in general of the European option discounted. So here you have the two discounting factors, and you can play the same for the European put option, right? So then you have the same here, was changing the payoff profile, payoff function here to the put option. Okay. 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 So how do we get now the equality? Well, now I just need to calculate here the left-hand side and see that I get the right-hand side. So if I consider the difference of the price of the European call option at time t and the price of the European put option at time t, well, this is BT. And then I have multiplied it with the conditional expectation and the Q of the difference of these two payoff functions here. So I have the call one minus the put one divided by discounting factor B capital T discounted to FT. Okay. Well, now I can look at this difference. So this is here now just a linear function. So I get Pt minus Pt. Right, that's great. And now we are basically done, right? This is, so I use that the price process is a martingale under Q, so the martingale under Q, so I get here where the martingale property is, and this K divided by T is a deterministic process, so this is just what it is. Now I multiply this out and I get what I claimed, which is this. Right. So here we are. Quick proof for the put call parity in the European case. Okay. And now I want to understand how this translates to the case of American put and call option. So now let's divide by CAT, right? is the price of the American call option at time t. And the same PA is the price of the American put option at time t. So what do we get now as the new version, I mean, of the American version of the put call parity? And this is the content of the next lemma. Make it more precise. So we assume we have an underlying market, which is assumed to be finite. I want to have access to my fundamental theorems. It's arbitrage free, otherwise it's useless. And I want that it's a complete market. Right. That's good. Cool. And now I consider two American options. American. One is a put one, and the other one is a call one. So that I'm able to compare them, they should have the same maturity T and the same strike price. Okay. And then what we observe, so ST minus K is less or equal than the difference of the price of the American call option minus the price of the American put option. And this is less or equal than the right-hand side of the European identity. This is less or equal than ST minus BT divided by B capital T. So just scroll up again to the European one. So here you had the equality. So the equality you had here for the European one turns out to be now an inequality, but you also have the lower bound given by ST minus K. And this solves for all T and T. Okay. Right. So let us prove this inequality now. Okay. How do we go? Color. Let's say green for a minute. So what do we want to do? Well, we want to prove two inequalities, actually, right? So this is the first one. This is the second one we want to prove. So let's start with the first one. The second one is actually easier. So, okay, first what we learned is that American and European call option coincide. Right? Because if you remember, this is what we just learned. If you have an American call option, you will hold it anyway until the end, and this assuming with a Russian investor will happen, so the option are the same. No one will exercise it before maturity time. So what do we get from this? And also the price of the American call option and the American put option are the same. So if I look at CT, so I consider here the American call option, and I add K. Right? I pull this K on the other side. I know this is the same as the price of the American European call option at time t plus K. And now, as we were already discussed for the put call parity, well, I have the pricing formula for my European price, which is given by the conditional expectation under the martingale measure Q. Then I have to discount properly. So that's here. I get, right? And here the K, I mean, I don't need to discount it, but I have added a 1, multiplied with 1, so I didn't change anything. Right. Okay, so that's what I always have. And now what do we note? So let's, I mean, what we want to estimate this, I mean, this identity here from below, right? So we want to estimate it from below by ST plus the price of the American put option. So let's try to estimate this here from below. And here we know two things. The first one is, I look at here, PT plus K T. So this is the random variable here inside my conditional expectation. Well, I can estimate it from below by KBT, right? Because well, this summand is positive, so I can just forget it and estimate from below. Now I have a second estimate. Oh, this has to be multi. Right, I mean, my BTs are assumed to be increasing, so I can estimate this actually by making the second sum a bit smaller by dividing by B capital T. Right. And now, well, this is here we hit the same, so I can estimate this from below by S time T divided by BT. Okay, that's great. Okay. So now let's take an arbitrary stopping time. Stopping time. I have tau in set of stopping times, and I want that tau is less. I mean, it's the tau is at least it's T and smaller than capital T. Okay. So what do we get here? Right. So let's now take, well, these two identities here and take the conditional expectation of it. So right, we have here 1, 2. We take the conditional expectation under the martingale measure Q with respect to the iteration at time tau. Well, this is deterministic constant, and tau is bigger than t, so I can estimate this by t. And this is a constant. So if I take here the conditional expectation, it just doesn't affect the right-hand side. So this is the first thing, and I do the same for the second inequality I derived here. So I have this divided by bt plus k bt conditioned on f tau, well, can be estimated now by our optimal stopping theorem. So I have to take the conditional expectation with respect to ft. So this is the martingale under q. So I get s at time tau divided by b tau. Okay. Okay, now let us plug in these two estimates together. So what do we get if we combine these two estimates? Well, what we get is that this quantity here can be estimated from below by the maximum of the first estimate and the second estimate. Well, this, I mean, if this maximum is nothing else than here my European to payoff stop that time tau discounted by t b tau plus s tau normal. So the discounted price process at time tau. All right, so let us come back now to our quality where we started with. So so if we plug this in now, wait, let's call this star star. So let's keep green, combining star and star star. So we can estimate here the sum of the price of the American call option at time t plus k by and now we plug in what we have here. So let me drop this step. So we plug in what we have here plus s tau divided by b tau at time t, right? So up here, this is exactly here the left-hand side of star, and then I estimate the inner term, so the random variable inside the conditional expectation by using the tower property and then the estimate I made here. Okay, and now I can further calculate this. Oh, sorry, I forgot this counting vector. So I have my counting vector, and now it's here. Plus dt, the condition on ft. And for the second one, I used the martingale property of this go-to price process to see did I get yes. Right. And now I recall where we started today in the lecture. To see, well, this is nothing else than the price of the American put option. So this is the first inequality we wanted to prove. If we go up here, so okay, we proved the rearrangement of it. So we proved that the price of the American call option plus the strike price K is greater or equal than the price of the American put option at time t plus the price of the risky asset at time t. Now we want to prove the second one so that we can estimate the difference of the price of the American call option minus the price of the American put option by here the right hand side. Oh, where's here? Okay, so this is, as I promise you, it's not too hard. So let me finish with this proof. Second, because we can now just use the put call parity for European options. Right, so if I consider the difference of the price of the American call option minus the price of the American put option, I can, I can do the change for the European call, right? The American and European call option are the same. So I can change the A here to an E. And now I know that my American option are always more expensive than the European one. So I subtract less if I make here replace the price of the American put option by the price of the European call option. And now I apply my put call parity with the European options, which gives me the claimed right-hand side for T in T. Right, and this finished my proof here. All right. All right. So this is, I think, all I wanted to do here for the American and European call and put options. And next time we briefly discuss the case of pricing hedging in the incomplete market. And then we go on and start about portfolio optimizations problems. All right, thank you very much, and well, hopefully you stay motivated and follow the lecture.